Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be going over an introduction to problem solving. In particular, we're going to look at applications of linear equations in single variables to solve real-world or application-based problems. We're going to start by reviewing the Polya method for problem solving, a technique that we can use for any of these application problems that we're working on. Then we're going to go over two types of applications. We're first going to look to see about taking given information and turning it into a written equation. And then we're also going to look at a common type of application problem in algebra, the consecutive integers problem. So first up, let's talk about the Polya method for problem solving. This is a technique in which it's recommended to do several different steps when you're in a problem-solving setting. When you have to solve an application problem, a word problem, these are the recommended techniques we're going to use. First up, you have to read the problem. Oh, wow. That is very insightful. We have to read the problem? Well, of course you have to read the problem before you can do a word problem. But it means more than what it just says. You first should skim the problem. If you're given a word problem, the Polya method says first skim through it. Once you skim through it, ask yourself, what am I trying to find? What is the specific piece of information I need to know for this problem? Once you identify what you need to find, and you've gotten a general idea of what the problem is asking, then reread it for detail. Okay? Here's where students tend to make their first big mistake. When working on a word problem, I find a lot of times that students just read through the problem once and that's it. And they try to commit everything to memory that first time. You can't do that, especially in much more complicated, elaborate problems. You have to reread it several times. So this will be helpful to us. Read it through once and just get the main idea. What's going on here? What's this type of problem? What's the setting? What's the plot to this problem? Then you ask yourself and really identify, what do I need to find? Once you know what you need to find and you got a general sense of what the problem is about, then read it for detail. Then you'll start picking up on the key information because you'll be saying to yourself, oh, okay, this will help me solve for that missing information. So once you've really read the problem and you got an understanding of what we're supposed to do, develop a plan. To really come up with a plan, and that can be kind of vague, can it? Come up with a plan, figure out what you need to do. We should really start by identifying what the key information in the problem is. Look for what were we specifically told? What details were we provided? Is this like a geometry problem? Were we given specifications of a shape or dimensions of an image? Is this an algebra problem? Are we given a rate of change or some type of pattern information? Figure out what is key to the problem. Then it might be helpful to figure out what info you're not given. Think about what you're trying to find. You've already identified, what am I specifically trying to find in this problem? That might help you out when you are thinking about what that information is. Maybe this is a geometry problem and you're trying to find a missing side length. Okay, I'm trying to find a number that is a measurement. Or maybe you're trying to find a degree measure. And then you're saying to yourself, okay, I need to find a number that's a degree measure. By knowing that, it might help you in developing your plan because you're thinking about what plan of action will give me this specific type of information. And then some techniques that are helpful when really trying to come up with a plan. Think about doing stuff like maybe drawing a picture or making a model of what the situation's going on. You're being described information. Maybe you can model it out on paper or draw a picture of what's going on. One technique that can be very helpful is diagramming the sentence. And we'll talk about that in just a little bit. But basically, it's taking written information or verbal information and putting into mathematical symbols. Once you have your plan for what you're going to do, you then implement the plan. Go ahead and put it into action. But please make sure that you use proper mathematics. This is another big issue that students tend to have. They come up with a plan and they might not be doing proper math. Like I've seen students, they'll come up with a plan and I'll say, wait a minute, you're adding a number to one side that you're not adding to another side. That's an issue with the additive property of equality. You can't do that. Or they'll be doing distribution, but their plan only distributes a number through to some of the terms, but not others. It's like, well, you can't do that either. You can't just take properties and change them around so they fit what you want to do. You have to use proper mathematics. And please make sure that whatever your plan is, whatever you've decided to do, make sure that it's not something that you just came up with and have no idea if it works. A lot of times when people are trying to figure out what to do, students will just come up with some plan out of nowhere, and I'll ask them, okay, how do you know if that works or not? And they'll say, I don't know, I just thought of it. Now, there's nothing wrong with coming up with something on your own and thinking that maybe this will work and trying it out. That's totally fine. But if you're going to use a plan that you're really just coming up with, if it's not something that you've gone over in class, or it's not really something that you've done before, you really want to make sure you vet your work, okay? You really want to make sure you go through and that it's using solid math, okay? Don't just do something without ever having done it before and then just assuming it works, okay? Really make sure, think about it, do some practice problems with it. Try to see, can this work out? Before you just do it and call it a day, okay? So, typically that's where we would normally stop in a class. We've read the problem, figured out what we need to solve for, we came up with our plan, and we put it into action and got a solution. However, the Polya method says don't stop there. A really big, important aspect to problem solving is reflecting on the problem and your work. You need to go through and reflect on your work. Sometimes people say this is like checking your work. But also, I want us to take it a step further. We really need to think about our methods and our techniques. For example, ask yourself, was this what I was supposed to find? You got a solution. Was that the proper solution? Was that what you needed to achieve? A lot of times students will get an answer and I'll say, well, wait a minute, what were you supposed to find? Like they might, for example, in a class, they might say, oh, I got this number of inches, right? I solved this problem and my solution is 5.6 inches. And I'll say, wait a minute, what were you supposed to find in the problem? And they say, oh, a missing angle measure. And I go, wait a minute, if you're supposed to find a missing angle measure and your answer is some length of inches, that's not the same thing, is it? And then they realize, oh no, I solved for the wrong thing. Or what I got from my solution is not what I needed to find. Sometimes this happens like in a science class when students are supposed to find units of one solution, they find the units of another solution. People don't always see beyond they just got an answer, right? Their process spit out a number and then they stop thinking. We don't want to do that. We want to make sure that what we got is what we started out looking for. So that's a big part of reflecting, okay? Besides just checking your work to make sure you did proper math, check to make sure that overall it was what you wanted. Additionally, something to think about. When you reflect on a problem, and especially the plan of action that you took, what were my assumptions? Think to yourself, because anytime you do a word problem or an application problem or use problem-solving skills, whatever you want to call it, you come up with assumptions. You have assumptions right away. Some of them you were told in the problem, and those you can assume to be true, right? However, when it comes to other aspects of problem solving, we oftentimes assume certain things are true. That could be an issue. We want to identify to ourselves, what did I assume about this problem? And then think, could my assumptions have affected my solution? And should I account for that? Should I keep trying to solve this without having these assumptions, or were they valid assumptions to have? We'll talk more about this as we get into more complex problems. But for the time being, really, before you just get a solution and write it down, I want you to go ahead and reflect on that. And think, was this what I set out to find? And then we'll have completed the Polya method of reading the problem, developing a plan, putting that plan into action, and really making sure that that plan was done properly. Now let's go ahead and use this Polya method to try to take written information and convert that into symbolic format. This is a standard when it comes to problem solving, right? You talk about a problem with people, you get it written down for you, and it's in a language like English, right? It's in the language we communicate with. But the problem is we need to take that information and we're going to have to now put it into mathematical symbols. Symbols meaning numbers, variables, general structure and formatting like an equation. We got to see what we're given here. So let's read this problem. The sum of a number and negative 11 is negative 15. Find the number. All right, we read it through once. We got an idea of what's going on. We're told some information about numbers and their relationship. What are we supposed to find in this problem? Well, you can always in problems look to the last sentence, and you can see for yourself, they tell you what you need to find. So in this case, we need to find a number. That's what we're looking for, some number. Okay, but that's not that much detail, is it? Well, you could say we need to find a number that satisfies all of this previous information. So now let's reread this problem, keeping in mind that we're trying to find a number that satisfies these relationships. So the sum of a number and negative 11 is negative 15. The sum of a number and negative 11 is negative 15. Okay, a lot of little details in there. The method that I find particularly helpful when going through a word problem, and it's to find all that key information that we need, is to diagram the sentence. What I mean by that is I mean to highlight, underline, circle, really whatever you need to do to identify what's the key information to the problem. Whether that's key information in terms of numbers, or that's key information in terms of formatting the numbers. Let's take a look here. Let's go through this problem, and I'm going to underline and circle some key words and phrases. Let's start with the sum of. Sum. That's a word we use in mathematics, isn't it? The sum of, a number. Okay. That was kind of making me think of what I'm trying to find, right? So we have the sum of a number and negative 11 is negative 15. Okay, so they're using words to tell me specific numbers. I have some operations I'm being told as well. So let's try to start putting some of these written words into symbolic format. First up, let's identify some of these key phrases. Sum. What does sum mean? Well, sum means addition. You've added multiple things together. So we're going to say addition. So what have we added together? Well, let's see. The sum of a number and negative 11. So the two things we added together were a number and this negative 11. So negative 11, we already know what that symbol is. We know how to write that as a number. But then we have this phrasing here, a number. What does that mean? A number. Which number? How do I use that? And in fact, that's the thing I'm supposed to find, isn't it? A number. So what do we do with that? If I don't know what the specific number is, what can I write for it? Well, hopefully you're saying, make it a variable. You don't know what that information is, right? You're not told what number it is. And in fact, that's what you got to find. So you have to use a variable for it. So we have sum of a number, we're going to call that x, and negative 11 is negative 15. I want to highlight here the word is. When you are working in mathematics, the word is represents equals. Let me write that a little neater. It represents equals. You can actually sub the word equals in for the word is. You could say the sum, that's addition, of a number and negative 11 equals negative 15. And in fact, I'm going to say any verb in the sentence, like it could, and this being a being verb, but you could have things like anytime you say the sum of a number and negative 11 is, if you say approximates, equates to, measures, achieves, anytime you put these verbs in place, it means equals. The most common verbiage that we use in English is the word is. So when I'm working through diagramming a sentence, I look for that word is. What's very cool about this, anything to the left of the word is on the left side of your equation. Anything to the right of the word is on the right side of the equation. That's a cool thing about the way in which we structure English and how it's related to the mathematics. So, if I were to take this and put it into an equation, I'm going to look at with that word is. I'm going to put my equal sign down. All right? What was to the right of the word is? Negative 15. All right, that was it. So that's my entire right side of the equation. What about the left-hand side? What was to the left of the word is? Well, sum of x and negative 11. So we took x and negative 11 and we've added them together. That phrasing came to the left of the word is. That's why it's on the left side of my equation. This word is actually does, in English, separate the two sides of the equation, okay? You're not going to have words over on this side that end up on the left side of the equation. That's not going to happen here, okay? So that's a really cool thing to have when we're starting to try to structure this. So here we go. We have our equation. We have the sum of a number and negative 11, and we have that equal to negative 15. So we can go ahead and actually solve this. Well, let's add 11 to both sides. That'll cancel out. We have x is equal to negative 4. That is our solution. X is equal to negative 4. In fact, okay, let's reflect on this. Negative 4 is a number. Well, okay, maybe that's not the most, that wasn't the most descriptive problem, but we have negative 4. It's a number, so we got what we needed to find there. And does it satisfy this problem? Maybe it would be helpful to change every time you see a number in here to negative 4. And let's see if it works. The sum of negative 4 and negative 11 is negative 15. Is that true? Well, yeah, it is in fact. So we're pretty confident that we have the correct solution here. Did we use proper mathematics? Yeah, I added the same thing to both sides of an equation. I was allowed to do that. And I know that the sum of 11 and negative 11 are going to cancel out. So we were just left with a single x is equal to negative 4. So we did proper math. We found what we wanted to find. We checked it out, and it actually does work out. So we're probably good here. Now, any assumptions in this problem? Any assumptions? You can say we did make some assumptions. One of the things you can say is we assumed we were working with real numbers. Okay, that should be fine. And we can also say we were assuming that we would just have one solution to this problem. We do just have one solution to this problem, and we are working in real numbers, okay? Those weren't specified anywhere in here, but generally speaking, I would assume if I asked most students, they would say there's one solution to this problem, and we're dealing with real numbers, right? Numbers that could be anywhere on the number line. So whole numbers, fractions, decimals, etc. So in this problem, it's fairly simple to say that no, our assumptions really didn't affect any of our work. What I'd like us to do now is go ahead and practice diagramming these two sentences. Actually go through and read the problem, identify what you need to find, and then reread it for some detail. As you reread the problem, underline, highlight, circle, star, whatever you need to, the key information. And again, that key information you're looking for numbers, variables, operations, and you're looking for the word that symbolizes the equal sign. Maybe it's is. Maybe it's another type of verb, okay? Try to see if you can go through and diagram these two sentences, and then we'll check our work together. All right, well, hopefully you had some time to work through this, and you're starting to feel a little more comfortable with it. In the first problem, we're going to need to find a number. And again, we're not given much detail. All we know is that it needs to satisfy all of this previous information. Okay, let's read this information and let's highlight the operations and the numbers we're going to be working with. So, 40 less than 5 times a number is 52 less than the number. Okay, first thing I'd like to do, I saw the word is. I'm going to circle that. I'm going to put an equal sign there, okay? Because this is now the structure to my equation. I have the left-hand side, and I have the right-hand side of the equations now. So let's pick a side and start working with that. I'm going to start with the left-hand side. 40 less than 5 times a number. Oh boy. Okay, well, let's see here. A lot of details. Less than, if you remember, implies subtraction. In times implies multiplication. I'm going to do, in fact, this symbol, the asterisk symbol for multiplication. Let me see if I can make that a little neater. I don't want to use x because we're going to use that for a variable. So we're doing some subtraction and we're doing some multiplication. What numbers are we subtracting and multiplying together? Well, we have 40, we have a 5, and then we have a number. Okay, that's going to be x. If I can't specify what that number is, it's going to have to be the variable. And that's what we're trying to find here, isn't that? X. Okay. We've got the left-hand side pretty well diagrammed. We've identified the operations and the numbers. Let's do the right-hand side now. We've got 52, so we know that number. And then we're saying less than the number. Okay, less than implies subtraction. And then we keep saying the number. Well, that's x. All right, again, we've identified the variables, the numbers, and the operations. Let's start putting this all together in an equation. I'm going to start with the equal sign. That's the is here, okay? So here's the equal sign. Let's do the left and the right-hand sides. Let's start with the right side. 52 less than the number. Okay, we're doing subtraction. And what are we subtracting? 52 and the number x. But wait a minute. Is it that, or is it x minus 52? Oh, shoot, which one is it? Does it matter which order we do subtraction in? Well, yes, it does. Okay, we have to be careful with this. So we need to say here, are we taking 52 minus x, or are we taking whatever x is and subtracting 52 from it? Let's look at the phrasing here. 52 less than a number. Let's try to reword this. Maybe let's make this a little easier. Let's use single-digit numbers like 2 and 5. Let's say something like 2 less than 5. What is 2 less than 5? Well, 2 less than 5 is 3. Because we took 5 and we took 2 less than that, so we get 3. We didn't take 2 minus 5 to get negative 3, did we? Because 2 less than 5 means this first number is what I'm subtracting from the second number. So that's a thing we have to be careful with in our phrasing here. So in this situation, when we say 52 less than a number, we mean take the number x and subtract 52 from it. Take the second number and subtract it, or sorry, take the first number and subtract it from the second. X minus 52 is the right-hand side of our equation. Now let's take a look at the left-hand side. This one's a bit more complicated. 40 less than 5 times a number. Okay, we have some things going on here. We got multiple operations. We're subtracting some things. We're multiplying some things. And we have the numbers 5, 40, and then the variable x. Well, what order do we do this in? So let's see here. 40 less than. That means we're subtracting 40 from the second number. So are we taking 40 less than 5? So 5 minus 40, and then times x? Is that it? 40 less than 5 times a number. Well, 40 less than 5, and then we're going to times that by a number? Or does it mean 5 times a number, and we're taking 40 away from that? I will tell you right now that the correct solution is the second one here. 5x minus 40. And here's why. We're saying take 40 less than something, okay? So obviously, we're subtracting a number by 40. Is that 5 or is it 5x? The reason it's not 5 minus 40x is because I'm not saying take 40x off of a number. I'm saying take 40 off of this product, this 5 times a number. That's what we're saying to do here. So think back to your order of operations. Multiplication is going to come first here. So we're going to have 5x minus 40. Let's go ahead and solve this now. Let's subtract x from both sides. And in fact, you know what? Let's add 40 to both sides. 5x minus x is 4x. And negative 52 and positive 40 is negative 12. If I divide both sides by 4, we get x equals negative 3. Let's go ahead and actually put this in every time we see a number, and let's see if this works. So instead of having x here, I'm going to put in negative 3. Instead of x here, we're going to put in negative 3. 40 less than 5 times negative 3. Okay, 5 times negative 3 is negative 15. 40 less than that, so 40 subtracted from negative 15 is negative 55. Okay, that's what this side should be, negative 55. And then on the right-hand side, it says 52 less than negative 3. So negative 3 minus 52, yeah, that should give me negative 55 as well. So it works. If we plug our solution back in and we check our answer, it actually does work out. Any assumptions that we made here, well, you could have assumed we were working with real numbers, or maybe you assumed we were working with integers. You assumed there was going to be one solution. None of that really played into the overall setup, right? We just took the information and put it into an equation. So we're good there. Let's take a look at the next problem. Twice the sum of a number and 6 is 2 more than 3 times the number. All right, there's that keyword is. That's my equal sign. So I'm going to write that down. Let's work on the left-hand side first. Twice the sum of a number and 6. Twice, that means 2 times, right? And then we see the sum of, that means addition. So we're taking 2 times something, and you know what, let me write this as an asterisk. I'll write that a little neater. 2 times something, and we're adding some things together. So what numbers are we working with? A number and 6. We have 6 and don't know what that number is, so it's a variable. So let's take a minute and think, how do we structure this? We're working with x and 6. We're asked to add them together and to multiply them by 2. But how do we order this? What order do these things come in? Twice the sum of a number and 6. Twice the sum of a number and 6. Twice the sum. We are being asked to multiply the sum by 2. And we're being asked to add together the number and 6. And we're being asked to double what that sum is. That means wrap the sum in parentheses and then multiply it by 2. When we're asked to do two operations, these are what I call embedded operations, where you're asked to do one first and then the other. Generally speaking, you're going to need to use parentheses here because we're asked to multiply 2 times the sum. I don't want just 2 times x. I don't want 2 times 6. I want 2 times what their sum together is. Generally speaking, the inner operation, here that's the addition, is what comes first. The outer operation, the first one that was listed, is what's on the outside here. Generally speaking, that's how this tends to work out. Really, you need to say to yourself, okay, what am I being asked to multiply? What am I being asked to add together? Here I asked you to add together 2 numbers, and then once those were added, I asked you to double their sum. So if I ask you to do anything with their sum, their difference, their product, their quotient, that means do those operations first and wrap them in parentheses. Now let's look at the right-hand side. 2 more than 3 times the number. 2 more than, again, that implies addition, and then we have 3 times, let me clear some space here. We got a few different operations going on here. So 2 more than, we're adding together, and then we have 3 times the number x. Okay, 2 more than 3 times the x. 2 more than 3 times x. 2 plus 3 times x. 2 plus 3 times x. Do you see what I just did there? 2 more than 3 times the number. We have our symbols in place, and I just started reading the symbols out. 2 plus 3 times x. 3 times x, and add 2 to that. Or another way of phrasing it, this is more literal. 2 plus 3x. We're not saying add 2 and 3 together and then multiply that by x. We're saying multiply the 3 and the x together and add 2 to that. These are separate operations. 2 more than, and then do 3 times x. That's it. I'm literally just writing down exactly what the sentence says. So hopefully this is making sense to you. You're getting in the hang of just diagramming the sentence and writing down what it literally tells you. And then some of these little techniques, like when we have embedded operations, twice the sum, right? When we're telling you to do 2 operations consecutively. So here's our equation. We can go ahead and solve this by distribution here. Let's see, I'm running out of room, so let me move this up a little. Let's subtract 2x from both sides. So we're going to have an x on the left-hand side. I'll subtract 2 from both sides, so I got a 10 on the other side. And that should be our answer. 10 is x. You can plug it in and check this. Twice the sum of 10 and 6. 10 and 6 is 16. Twice the sum of 10 and 6, so 16 times 2 is 32. So this left-hand side should be 32. Then the right-hand side says 2 more than 3 times 10. 2 more than 3 times 10. 3 times 10 is 30. 2 more than that is, hey, 32. Again, it works out. So hopefully we're feeling more comfortable with this. Again, a lot of this is just literal copying of what you're being told, right? And occasionally a couple trick or two, like what happens when we have these embedded operations. But generally speaking, yeah, we're just writing down literally what we're told in the phrasing. Now let's take this idea of being able to diagram sentences and the Polya method to now solve a very common type of application problem in algebra, and that is the consecutive integer problem. First off, we should define what consecutive integers are. Consecutive integers are integers that occur, let me write that a little neater, integers that occur one after, my stylus is kicking out on me, one after each other on the number line. Okay? So consecutive integers are integers, and remember, integers are positive and negative whole numbers and zero, okay? So we have whole numbers that occur one after each other on the number line. So they're consecutive. Things like 1, 2, 3, or something like 17, 18, 19. These are consecutive integers. They're numbers that are right next to each other on the number line. So in this problem, the sum of 3 of these consecutive integers is 156. What are the 3 integers? Okay, what do you need to find in this problem? We need to find 3 integers. Find 3, oh my gosh. Find 3 integers which are positive or negative whole numbers, or 0. 0 also counts as an integer. Okay, we know what we need to find. We're going to need to find 3 different positive or negative whole numbers. And since they're consecutive, we're assuming that they're going to be next to each other on the number line. So what does the problem tell us to do? We have the sum of these 3 integers is 156. Sum, that means addition here. Let me get some space for us. So we are adding up 3 consecutive integers, and that is equal to 156. So we have our equal sign, we have 156. We've added up 1, 2, 3 things together to get that. Okay, the question now becomes, how do we represent these 3 numbers, these 3 consecutive integers? Well, let's see, 3 consecutive, because we don't know what they are, do we? We're not even told one of the integers. Because, well, I guess if we were told one of them, then we would know the other 2, wouldn't we? All we know is that 3 mystery numbers next to each other on the number line actually added together to give us 156. Well, one thing that students would tend to do is they'd say, well, x plus y plus z, right? 3 variables, right? I don't know what any of the integers are, so we got to use variables for them. And since there's 3 integers, might as well have 3 different variables. While this is a valid framework of thinking, I'm going to let you know right now, this really won't work out. And here's why. If you're going to have 3 different variables, you would need 3 equations, at least 3 different equations, to solve for all 3 of the variables. Here we only have 1 equation that we can work with, okay? So this idea of having x, y, and z isn't a good idea. It's not going to work out. So we don't want 3 separate variables. In fact, since we're only working with 1 equation, we're going to want 1 variable. And that should make sense because we're in the unit that deals with single variable equations. We haven't learned to work with anything more than single variable yet. So we need a way of representing the 3 numbers, and we need to do this all with 1 variable. What I'd like you to do is pause the video, take a minute and think to yourself, and try a couple different techniques if you can. How can we represent the three different integers with a single variable. Take a minute and see what you come up with. All right, well, hopefully you're able to come up with some technique to work with this. Remember, we're trying to find a way of representing the three consecutive integers, all using the same variable. Some things that students tend to do when I tell them that is they'll put, okay, same variable, x plus x plus x. And then they say, okay, that's 3x, and there we go. We can solve from there. But hold on. Look at this setup. X plus x plus x. Aren't those three of the same number? Let's actually go ahead and solve this. 3x equals 156. If I divide 156 by 3, I should get, well, let's see, 3 goes into 15 5 times, and 3 goes into 6 twice, so it should be 52. So x is equal to 52. Okay. Go ahead and plug that back in. 52 plus 52 plus 52 equals 156. Check that on your calculator, and you'll find that, hey, it works. Yeah, 52 plus 52 plus 52 is 156. There we go. So 52 is our solution. Wait a minute. We needed to find three consecutive integers, not one integer. And that's what we did here. Our problem, our plan, I should say, was structured so that way we added the same number 3 times. No, these are not 3 of the same number. They're 3 different numbers. They're consecutive numbers, like 1, 2, and 3, like 60, 61, and 62, 100, 101, 102, things like that. They're consecutive. They're next to each other on the number line. So this setup of x plus x plus x actually won't work for us. So now we need a different technique. How can I represent these 3 numbers that equal 156 when I add them all together? One thing that can be helpful is to draw a number line and think of what it means to be consecutive numbers. Being consecutive numbers means that these numbers are next to each other on the number line, like 1, 2, 3, or like 57, 58, 59, etc. So they're next to each other on the number line, and I don't know any of them. So why don't I let the first number be x? All right, that first number is x. How does this help me? Well, what would the next number be? The number right after it on the number line. Well, I don't know. I don't know what that number is. But I know it's 1 more than the previous number. Wait a minute. It's 1 more than the previous number. If the first number is x, then the second number is x plus 1. What would this number be? Well, I'm not sure, but I just know it's 2 away from x. So that means it's x plus 2. If x is the first number, the second number is x plus 1, the third number is x plus 2. So go ahead and plug that in to the equation. X plus x plus 1 plus x plus 2. There is our setup for the consecutive integers. The key idea comes from understanding their relationship. Okay, if they're being consecutive, that means they're each 1 away from each other. So x plus 1, and then x plus 2. Now, you could have actually set this up differently as well. What if you said that the middle number was x? What would this number, 1 above it, be? That would be x plus 1. What would the number 1 below it be? That would be x minus 1. Okay? What if you said that this last number here, the biggest one, was x? 1 below it would be x minus 1. 2 below it would be x minus 2. All 3 of these setups would be valid. For that, I mean, you could have x plus 1 plus x plus 2. You could have x plus x minus 1 and then x plus 1. And you could have had x plus the x minus 1 plus the x minus 2. And all these adding up to 156. So all three of these setups would work. All three of these setups will give you the exact same solution. It is totally allowed and valid. I'm going to use the first one just because that's my preferred technique. I like the smallest number to be x and then work from there. Other people like the middle number to be x or the largest number. It's up to you, but all of them will work. So let's go ahead and solve this equation. Let's add the variables together. X plus x plus x is 3x. 1 plus 2 is 3. That's equal to 156. If I subtract 3 from both sides, I get 3x is equal to 153. And then let's see. 3 goes into 15 5 times, and it goes into 3 once. So it should be 51. And we're good there. So x is equal to 51. Hey, I got my solution. Or did I? Remember, we need to find 3 integers, not just 1. So I got one of them, 51. What comes after 51? 52. What comes after 52? 53. There we go. Now we have the 3 integers. X was 51. X plus 1 is 52, and x plus 2 is 53. We know what 3 things were added up to give us 156. And in fact, check that on your calculator. You'll see 51 plus 52 plus 53 does in fact give us 156. This is what we need to do when solving consecutive integers. The key is, how do you represent the different integers? Now let's try these 2 practice problems. The sum of 3 consecutive even integers is 174. And the sum of 3 consecutive odd integers is 279. Okay, we went and we structured the previous problem for consecutive integers, numbers that were next to each other in the number line. Now we're asked to work with consecutive evens and consecutive odds. These are even numbers next to each other in the number line, like 2, 4, and 6, like 16, 18, and 20. And then consecutive odds, like 1, 3, 5. 41, 43, 45, things like that. What I want you to do is pause the video and see if you can come up with the structure for these 2 problems. You are adding together 3 numbers to get 174, and you're adding 3 numbers to get 279. How do we structure this? How do we represent these 3 numbers? Again, you cannot do x, y, and z. You can't do multivariables because we actually don't know how to do that yet, and it wouldn't work out for this problem. You can only use one variable x. So, how do you structure this? Hint, try to draw a number line and use some examples. Make some examples of consecutive evens and consecutive odds and try to set up the relationship that you're seeing. All right? Take a minute and give this a try. All right, hopefully you did some examples of this and you're able to see the relationship here between consecutive evens and consecutive odds. What I'm going to do is draw a little number line. And let's pick some numbers. 1, 2, 3, 4, 5, and 6. Okay, let me do the evens in blue. 2, 4, 6, and the reds the odds I'm gonna underline in red. Okay, let's start with the evens. What do you notice about the relationship between even numbers? 2, 4, and 6. Remember, evens and in between them are the odds. How do we see this structure unfolding here? Well, hopefully you're saying even numbers are all 2 away from each other. You have to skip over the odd number to get to the even. So all even numbers are 2 away from each other. So let's say that this first even number, 1, 2, 3, 4, 5, 6. Here's an odd, here's an odd, even, odd, even. Let's say this first one is x, okay? That's the first, let me write that in red so we can see what we're doing here. That's the first even. Where is the second even? Well, it's 2 away, so it's x plus 2. Where's the third even? Well, it's actually going to be 4 away, so it's x plus 4. Here we have a way of representing the 3 consecutive evens. The first one is x. The second one, I don't know what it is, but I just know it's 2 away from that. And the third one, again, don't know what it is, but I know it's 4 away from that. And there's our equation. X plus 2 plus x plus 4 equals 174. So that means 3x plus 6 is equal to 174. You can subtract 6 from both sides and you get 168. And then if you divide that by 3, well, let's see. 3 goes into 16 5 times. And let's see, 1 would be left over, so then it goes into 6 times, so 56? Yes. X is equal to 56. Again, was that what we needed to find? No, we needed to find the 3 numbers. So we had 56 is the first one. The next one, the next even, would be 58, and then the next even would be 60. And there we go. We have our 3 consecutive even integers. That wasn't too bad. Now let's try it this time for the odd numbers. Let's try it for the odds. I'm going to change colors here. Let me draw the odd one in green. Okay. We can see, let's see here. We have odd, even, odd, even, odd, even. Again, they alternate in the same way. We'll start odd, even, odd, even, odd, even. I'll label these in red. Again, odds, we got to skip over the evens. So let's let this first odd be x. Okay, don't know what it is, but we're just going to say it's the variable x. How do we get to the next odd number? We have to skip over the even. We have to skip over 2 places. So it's x plus 2. And then how do we get to the following odd? We got to skip over 2 more. It's x plus 4. It is the exact same setup for evens as it is for odds, because they're spaced out the same way. Evens and odds are all spaced out the same. You got to skip over the next number. So you can see why drawing this number line here is pretty helpful for us to kind of visualize what's going on, to visualize how we need to actually go ahead and structure this pattern. So let's add these together. We get 3x plus 6 is equal to 279. If I subtract 6 from both sides, let's see, 279 minus 6 is 273. And if I divide by 3, let's see, 3 goes into 27 9 times, and it goes into 3 once. So x should be 91, and that works out. So if x is 91, let me write these over here, 91. The next odd number would be 93, and the next odd number would be 95. That was x plus 2, and that's x plus 4. We have our 3 consecutive odds. Consecutive evens, consecutive odds, they're all structured the same way. All that we're doing here is we drew a little picture, we drew a number line to help us see this relationship that we have between the numbers. So again, we read the problem. We figured out what did we need to find. We identified that, and then we found what was the key info. Then we had to ask ourselves, well, we need a plan. We need a way of writing this equation. More specifically, we need a way of representing these consecutive numbers. So we drew a number line to help us out. We pictured what was going on. And then got our solution, and we checked our work to make sure that it was correct. If you have any questions about this or comments about the video, please let me know. My email is klinford, that's KLINFORD, at wccnet.edu. Let me know what you thought or if you have any questions. And until next time, take care.